Okay, so before we get to the black hole, we need to talk about what makes one. And it starts with a star, a really, really big star. Stars like our sun burn for billions of years. They fuse hydrogen into helium in their core. Basically a controlled nuclear explosion that never stops. That's what holds them up. But really massive stars, we're talking 20, 30 times bigger than our sun. They run out of fuel way faster. In cosmic terms, they burn bright and die young. And then boom, the biggest explosion in the universe, a supernova. For a few weeks, this one dying star outshines the entire galaxy it lives in. And at the center of all that chaos, a point of matter so dense, so compressed, that nothing, not even light, can escape it. That's your black hole. Here's the wild part. The black hole itself isn't black because it's dark. It's black because light that goes in can't come back out to reach your eyes. It literally has no color. It's just absence. The closer you are, the steeper the curve. Far away, barely any effect. A bit closer, you orb. Really close, you spiral in. Past a certain point, you can't climb back out. Now, a black hole isn't a vacuum cleaner. It doesn't suck things in from far away. If our sun magically became a black hole right now, Earth would just keep orbiting normally. We'd freeze to death, but we wouldn't get eaten. Seriously, the gravity of our sun replaced by a black hole of the same mass, exact same pull, exact same orbit. Just no light, no heat, no life. The black hole doesn't care about you unless you get close. All right, so we've got our black hole. Now let's actually go look at the thing up close. Starting with the part that sounds terrifying, but is kind of fascinating, the event horizon. The event horizon isn't a wall. It isn't even a thing you can touch. It's just a line, the point where escape velocity exceeds the speed of light. Cross it, and physics says you can't go home. Let's go layer by layer, from the outside in. Think of it like peeling an onion, except every layer breaks your brain a little more than the last. First, the sphere of influence. This is where the black hole's gravity starts beating everything else around it. Stars, gas, dust, everything in this zone plays by the black hole's rules. The accretion disk is spinning insanely fast near the black hole. The photon sphere. This is the zone where light itself gets caught in circular orbit. Photons actual light going around and around the black hole like a racetrack. If you were standing there, you'd see the back of your own head. That's not a joke, by the way. Standing at the photon sphere, the event horizon, the point of no return. Here's the weird thing. If you were falling in, you wouldn't feel anything special crossing it. You just cross it, and then it's too late. The closer you get to a black hole, the slower time moves for you relative to someone watching from far away. That's not science fiction.
I've been here 1 year.
That's just what gravity does to time.
Dave's been gone 10 years.
Gravity bends light. This is called gravitational lensing. Black holes are so massive, they literally warp the path of light itself. If a star is perfectly aligned behind a black hole, its light bends around all sides equally, and you see a ring of light surrounding the darkness. Not all black holes are the same size. Stellar mass ones are just a few times our sun's mass. Intermediate ones somewhere in between. Still mysterious. Our galaxy has one, Sagittarius A star. It weighs about 4 million times our sun. We actually mapped stars orbiting Sagittarius A right at the center of our galaxy. In 2019, we took the first actual photo of a black hole, M87, 55 million light years away. In 2022, we photographed our own one, Sagittarius A star, the fuzzy orange donut at the center of our galaxy. So that's the anatomy. From outside in, sphere of influence, accretion disk, and we haven't even gotten to the really weird stuff yet. Okay, thought experiment time. You're falling toward a black hole. Just you. Answer it depends entirely on where you're watching from. Alex is falling in. These two people are about to have very, very different experiences of the same event. Sam watches Alex fall and sees something strange. Alex slows down and slows and slows. Her light gets redder and dimmer. But from Alex's perspective, she feels nothing unusual. Free fall is weightless. You feel like you're floating. Once inside, the whole universe squeezes into a shrinking bright circle in front of her. Here's where it gets painful. Spaghettification. The gravity pulling on your feet is significantly stronger than the gravity pulling on your head. The technical term is tidal disruption. The forces stretch you into an incredibly thin stream of atoms. Scientists actually call this spaghettification. That's the real name, in actual papers. We've actually watched this happen to real stars. A star wanders too close to a black hole and gets torn apart. Time dilation gets truly insane near the event horizon. If Alex could come back, everyone she knew would be dead for centuries. And at the center, the singularity. All of the original star's mass compressed into a point of zero volume. This is one of the most honest things in science at the singularity. We just don't know. General relativity and quantum mechanics. Alex reaches the singularity. What happens? We don't know. Maybe she's destroyed. Maybe quantum gravity does something we can't predict. Here's where it gets philosophically uncomfortable. Quantum mechanics says information can never be destroyed ever, but black holes seem to destroy everything that falls in. One proposed solution is the firewall. The theory that at the event horizon, there's actually a wall of high energy radiation. So the lesson here is don't fall into a black hole, even if the theory is interesting. Sam made the right call staying outside. Here's a fun one. If you fell into a supermassive black hole, billions of solar masses, the tidal forces at the event horizon, from Sam's point of view, Alex never falls in. She just freezes at the horizon, gets dimmer and redder, and stays there theoretically. If you were somehow surviving the journey and looking outward toward the universe, you'd see the entire observable universe compressed into a shrinking circle. And then she's gone. The black hole doesn't change, the universe doesn't pause, everything continues exactly as it was. Here's something Stephen Hawking figured out in 1974 that blew everyone's minds. Black holes aren't completely black. Quantum mechanics says empty space isn't really empty. Pairs of particles and antiparticles constantly pop into existence. The energy for that escaping particle comes from the black hole itself. Quantum weirdness effectively takes mass. Here's the counterintuitive part: the bigger the black hole, the colder and slower the Hawking radiation. In the far, far future, 100 billion trillion years from now, the universe will have gone dark. As a black hole shrinks from Hawking radiation, it gets hotter and radiates faster, which makes it shrink faster, which makes it hotter. In its final second, the black hole releases as much energy as billions of nuclear explosions. And what's left after? Nothing. The information paradox becomes urgent here. Where did all the information about everything that fell into that black hole go? We genuinely don't know yet. Stephen Hawking himself originally bet that information is destroyed in black holes. Hawking figured this out in 1974 during a period that he later described as one of the most exciting of his life. The full lifespan of a stellar black hole, born in a supernova, then it exists for 10 to the power of 67 years. For reference, all of human history, from cave paintings to smartphones to whatever comes next, would be an invisible speck. And the black hole just exists. It doesn't experience anything. It doesn't worry. We've never actually detected Hawking radiation. It's too faint. Scientists have tested the idea in labs using sonic black holes systems. White holes, the mathematical opposite of a black hole. If you time reversed all the equations of a black hole, you get a region of space that only pushes things out, nothing can enter it. Wormholes. Einstein's equations technically allow a tunnel through space-time. Problem. The equations show that an Einstein-Rosen bridge snaps shut almost instantly. Spinning black holes have an ergosphere, a region just outside the event horizon, where space itself is dragged around with the rotation. Quasars, a galaxy with a supermassive black hole consuming material so fast. We know stellar mass black holes formed from dying stars. We know supermassive ones at galaxy centers. But in between, intermediate mass, when two black holes merge, they release more energy in a fraction of a second than all the stars in the observable universe do in the same moment. LIGO is the most sensitive instrument humanity has ever built. Its 2 arms are 4 kilometers long. Our own black hole wasn't always this quiet. About 6 million years ago, Sagittarius A star was active eating material blazing with jets, the Fermi bubbles. Each one is 25,000 light years across, extending almost as far as the distance from Earth to the galactic center. Here's the wild part: black holes and galaxies grow together. The black hole feeds on the galaxy's gas. In about 4.5 billion years, our Milky Way will collide and merge with the Andromeda galaxy. Our sun will survive the collision. Most stars and galaxy mergers pass right through each other. What we'll have is Milkomeda. And here's what we still genuinely don't know. What happens at the singularity? Where the information goes, whether wormholes are real. Black holes are the universe's most extreme proof that reality is stranger than anything we could have invented. They break our intuitions, break our equations, and keep handing us new questions. And honestly, that's the best thing about them. We've been staring at them for 50 years, and we're still only getting started.